All right, so in class we jumped to the linked list implementation, blah, blah, blah. Wow, slides. There is a stack implementation of this, and a lot of times it is implemented with a stack. The idea is that the list points to the bottom, and then you keep track of a stack top, which points to where the top of the stack, obviously. Okay, great. Which is really the size. Now, these variable names are misleading. I don't like them because it's really not, I mean, max stack size, you're using the word size, but really the stack size is the how many elements are in it. Really the issue is this should be capacity because that's how many elements the array currently can hold. In this case, up to 100, or 99, index 99. And then stack top is the position in it or the actual size of the stack. So we have A, B, C, D, and you have stack top of 4. Let's see if they give you some nice picture. They do not. If stack top was 0, then that means the top is pointing here. And even though you have A, B, C, D, it's ignored because your stack top is 0. See back here, these are your stack elements. Goes stack top 4. Over here, there's no elements. Oops. Oh, look, it gives you code. That's cute. So how do we push? Well, now we're going to change the letters. S-U-N-N, they probably want to add the Y to make it sunny. Where would the Y go?
On the top.
When you say the top, which top? I see 2 tops. There's 99 and there's 4. 4, right. Sorry. Not trying to be, well, I don't know, obnoxious. We just need to be precise. All right, so we put the Y here, and then what would we do with our variables? Will we change any of them?
Yeah, stack top would go up.
2, 5. Boom. Everybody got that?
Mm-hmm.
All right, so they wrote some code. Great. Well, they didn't talk about pop. What happens if you're at 99 and you try and push something?
Segfault.
Oh, well, the stack shouldn't segfault if you keep pushing to it unless you really are out of memory. Are we actually out of memory? I'm sorry, we're not actually out of memory, just the stack doesn't have the capacity. So what could we do?
You could run something to extend the array's size.
How would we do that?
I'd much rather do a check and see if it's too big.
Well, you have to do a check first to see if it's too big, right? And then once you find out that you're at capacity, aka the stack capacity is full, what could you do in order to actually have a stack of 101?
Make a new array, delete the old one.
Make a new array, copy everything over, delete the old one, yeah. Don't forget the copy part. Otherwise it's going bad. All right, so let's go up here and do our handy dandy stack. We have the array version, and we have the linked list version. And let's do push. What's the big O of push on an array?
Just 1, right? He's going to the top.
O of 1 in which case?
If it's pushing to the top.
We got best, average, and worst.
What if it's not full?
Right, so, right, O of 1 and best and average, because on average, it's not full, right? So I'm just going to do B and A, O of 1. What about worst case?
O of N.
Why is that?
Because you're gonna have to, because when the stack is full, you're gonna have to allocate a new array, and you gotta transfer everything over.
Right. It's that transferring over that makes it O of 1, because you got to go 1 by 1 and transfer it. So in that situation, it's worst case O of N. How about a linked list?
O of 1.
O of 1. And is there a worst case? you just create a new node and put it in the front and we're done, right?
Yeah.
Yeah, so it's always O of 1. Hopefully it should be obvious which way you want to go. But anyways, actually not yet. All right, so let's talk about pop. Okay, are they going to show pop? So stack before popping D in an array, what would you do? Decrement stack top. Is there any case, are we going to have any issue like with push where we have, how do I even say that? In push we don't have, the array isn't big enough, so I guess pop, the array is too not small enough? That doesn't make any sense. Anyways, it doesn't happen. Oh, what? How about a linked list? Thought I saw someone say it. O of 1. And this is. Oh, okay. That's looking good. Alright. And they talk about copy stack, constructor, deconstructor, overloading, don't really. And linked list implementation. And this is what we did in class. We call it the head pointer, empty stack, and then every time you create a node, you just put it up front. So if you want to push a node, you create a node. Ooh, did we get a picture? Oh, sweet, look at that. So here's our stack, A, B, C. We create a new node to add, call it D. Set up D to point to head, and then have head point to D, and we're done. This look familiar?
Just a little bit.
Just a little. Good. How about to pop? Hey, there's that temp pointer. Move head down by 1 and then delete temp. Look familiar?
Yeah.
Oh, good. All right, there's one last operation that we didn't talk about, and that's peek. You need to find the top of the stack on O on an array. What's the big O?
Just one.
Yep, O of 1. How about a linked list? Yeah, can you just jump to the head point? All right, from this table, which way does it look like which you should use for a stack?
Linked list.
A linked list. All right. I'm going to see if I can explain why that's not always the case.
The array has lots of smaller O's of O ones.
Smaller O1. Yes, that's basically what it comes down to. The array has smaller O of 1s. If you actually look at the implementation of our push, we have to allocate a node. This is not, it's not super expensive, but it's not cheap, right? This takes time to do. In the array, you only allocate if you are in your worst case scenario. So most of the time, the array's O of 1, aka this, is faster than a linked list O of 1, which is why most of the time for a stack you are using an array. But hopefully you can see just from the code, it's actually kind of easier to implement it as a linked list. So it's up to y'all which way you want to do it. Because you know what your lab is, right?
Simplify it.
Good, I'm glad.
That was just a random guess.
Good talk, guys. This pattern is not going away anytime soon, just so you know. All right, but we are going to talk about a different data structure because that would be really short for today.